Good evening, can you hear me? Sudhanshu, can you introduce yourself? Maybe I can get to know about today. I'll be covering the final last week sessions portion which covers acoustics and also lighting design. Overall, this whole building science principles and applications course covers three different areas. Actually, four. You can say how the solar geometry, how it works, the climate classification, heat transfer mechanism. So the first part we covered more about solar geometry and also most about thermal science, and then further we moved on to building acoustics, where we deal about how we can know about sound and then how sound functions in building and what are the useful ways we can manipulate sound inside a building. And finally, we'll also be seeing about lighting design. And this course actually covers very little portion about lighting, where we talk about lighting source, the characters, basic principles of lighting, and how we design lighting, daylighting. And in terms of daylighting, we this portion covers, but there are other parts where how you simulate lighting and what are the various methods mathematically, how you calculate lighting inside. And there's one large separate portion on interior lighting, where you use artificial lighting, different types of lighting output they produce, and their uh, the illuminaries design principles that go under all these things is not covered in this portion.
Yeah, excuse me, sir.
Yeah.
So I basically had a doubt regarding there was this numerical that was there in assignment two, which was
Mm-hmm.
to determine the U value, and I think they had cancelled the doubt clearing class for this.
And it's
So
no,
and
it's not like that. You can ask the doubt now also.
no, yeah,
So
that's why no that for that week I was a bit busy last week, so I couldn't attend that
you can.
class.
I can
So
always explain in this class
yeah,
also. You can
so
ask. Uh,
yeah, so basically
Basically, I
I want to know
actually already
how
during
do
that
you solve
session.
this?
Hmm. So already last session we had that same
Okay.
question.
Yeah,
Third
I
week
was,
someone
yeah,
joined and then they asked the same question what you're asking now.
yeah, correct.
I remember correct. It's like you were given with multiple resistance per inch, something like that, right?
Yes, multiple
Multiple
resistors.
resistance
Yeah,
per inch you would have been given,
yeah,
and you would have been asked to find the U value.
correct.
So in general, how you find U value is equal to 1 by the total resistance.
Okay.
And what is resistance? Just imagine what is the unit of resistance. It's meter square Kelvin per watt. Okay, it's basically you would have been given. Can you just go? Can you can share the screen also of the question? It will be more easier for me to explain.
Um,
If you're not, if cannot, I'll also share the screen. I'm just looking for the particular. I have to open the portal. It's very simple thing. You would have been given thickness. You just multiply the thickness into the resistance. It's like in general you would think in electrical sense also. No, it's like the larger the thickness you have, the harder it is for the heat or electricity to pass through. So you just multiply the thickness with resistance. You will end up with actual resistance value. Here the data that have been given to you is resistance per inch. I remember. you multiply them with their respective thickness, and you finally add each one's resistance value. You will end up with the total resistance. Then you take reciprocal. You will get U value. Did you get it?
So could you solve it and show it, please?
So, okay, I can show. We go to Victo. Okay, basically there is determine U value of the following wall, which comprises of just skip this. Mhm. We reshare the screen. You can see the screen.
Yes, sir.
Okay. You have 1.1/4 inch thick hardboard, and the hardboard is given per inch. Here it's given as resistances per inch. Okay, you just multiply 1.8 with that 1.25 inch. I'll just like again to. Can you like you have a calculator or something?
Yes, sir. I'll just do it.
0.25 into 0.18. 0.045. I'll just here we take as first one will take as inside layer. Okay, from inside to outside will go. Ri is given as directly you just consider 0.68 because it's an coefficient thing, and R1 will take R1 which is hardboard 0.8 into 0.25 is 0.0045, sorry 0.045 I guess, yeah. Then R2 it will be 2-inch thick polystyrene which is also 8, right? Expanded polystyrene, and R3 equal to 1.25 into 0.75, 0.9375, and finally we have RO 0.17. Total R. Just add all these 6.17 plus 0.045 plus 8 plus 0.68, 9.83. Good evening, I'm just explaining week 2's U value calculation problem. Now later we'll just go into some concept related to. Can you see the screen? Sudha, Sudhanshu.
Yes, sir.
So we arrived at total R value of 9.83, no? Till that you are clear.
Yes, sir.
Then we have to do UL is equal to 1 by R equal to 1 divided by that 9.8 something. Then it will end up getting something around equal to 0.1 watt per meter Kelvin. So you understood it?
Yes, sir. Understood. Yeah.
Okay,
Thank you.
okay. Ah, now, okay. Any other doubts? We'll keep it in the last part of the session. I'll just go to the week's force. I'll just kind of concisely give a go through about it. Like week 3, actually, it started with sound, and sound basically needs a medium to actually propagate. Like if you have a vacuum space, sound cannot pass through, so it requires a medium, and then depending on the medium, in general, the medium the sound travel is air. So we just consider air and various terms associated with it we saw. And last week I also explained about like the relationship between all these terms of sound power, sound intensity, and sound pressure. And in any case, like we all start with any universal source in like a free field. So for like whatever we are speaking now, it will be like considering a free field. Even in lighting also, we kind of think it as a there is a point source from a free field. There is a constant source, and generally here what we speak about is sound intensity, and intensity in general it is measured in watts per meter square to for our general reference. But since sound intensity level it's kind of as a larger spectrum where we refer to, we try to refer sound intensity using levels. So this level actually see, no, wherever you see sound pressure made, whether it be sound pressure, or can others also admit? Okay, I'm just getting request. Whenever we speak, the term level comes, it relates to decibels. So if we have like sound pressure level, sound intensity level, we kind of use decibels for our understanding purpose. And last class we kind of saw about how to determine sound intensity and how different sound sources will finally result in a particular sound intensity level. Next, we also looked upon this LEQ, linear equivalent sound pressure level, where this sound pressure level, this is a kind of an indice. We use this indice to show that like if you have one room, L10 means whatever sound pressure level that exceeds a 10% of the total time, that gives one certain sound pressure level value. So based on this, we will be able to assess how loud or how silent a space is. And we talked about different sources of sound, like non-directional, which I told is like this in a free field area. When there is a sound, we use this, and if we have directional source, we have used this formula. And this there is a term associated called directivity, which associates to like what type of source and where the source is actually. It's basically depends on the location of the source. Imagine you have the sound source at the corner of a room. Imagine you have a small 3 watt speaker at the corner of the room. It will be more louder than you keep the speaker in an open field, like you would have practically seen it. Like if you imagine you have your phone only, you switch on the volume to highest possible level and you keep it in a free source. Its actual sound output that you hear from a distance varies. If you have a plain field, it kind of the decibel adds up to like 2-3 decibels compared to the free field non-directional source. And if you consider a corner room, the decibel increases by 9. And also sound is not just about loudness, and sound kind of like light, where we have different wavelengths and frequency depending on the wavelength, you kind of get a different color of light. Example, like something in the lower spectrum like 300 380, where you will get like violet to blue color light, and beyond this around like 700 nanometer you will get red color light. So these colors kind of you consider it as like frequency. Here also there is like a wider spectrum of frequency sound can be produced, and human can hear, they have a larger hearing capacity which varies from 20 hertz till it goes to 20,000 hertz, and the, you can receive different frequency sound at which the with which also has particular sound pressure level associated with that particular frequency. So here you see it's like a tuning fork. It kind of produces a low frequency sound with a high pressure level. But if we consider harmonics, you have multiple frequencies. And also if you consider a more complex sound where you consider an operation of a fan or air conditioner, you have various sound sources. Like, oh, can, can you see the screen? Excuse me. Mm, Let me reshare the screen. Please try to like intervene in between if you have any issues regarding the slides. Going back to this sound frequency and loudness level. These things we covered in the last class. Moving further, we also talked about noise criteria, where there are like different specific noise criteria level for each type purpose of space. You have like a living room where the conversation should happen, and it should have a noise criteria of below 60. And if you have a working space like office where you have a very silent environment, the recommended NC is like below 40 or below NC 35. Next one thing we saw about is the directivity of the sound, where the point source is being propagated at like the point source where it is originating from. That point of view we saw directivity. Another thing is sound propagation. Imagine if like a point source at a particular point has been emitted, it kind of travels over time, and depending on the nearby surfaces, the source keeps getting reflected. The reflection might not be like true reflection, like you have like 100% reflection won't be there, because the surface which is being hit will have a specific absorptive absorption coefficient associated with it. If we have a surface which has a very high absorption coefficient like 0.9, so if a sound source, if a sound source is like traveling towards that surface, only 0.1%, like 10% of the sound power level will be reflected back. So absorptivity of a surface greatly determines when the sound decays. So basically, if we have that particular point source, it will decay over some several milliseconds. In this case, like imagine you have like perfect reflective surfaces. The point source, once it's kind of start emitted, like you all know that sound propagates at a general air atmosphere. On an average, it travels at 343 meter per second. So based on that, you can kind of actually determine how much in how many milliseconds sound will reach to a point. And in this propagation diagram, you can see like the sound after like 16 milliseconds, the sound kind of reflects like maybe around like 10-15 times, hitting here and there. And since it's a omnidirectional point source, this reflecting part, we can just, it happens in all direction. For our understanding purpose, we just take, imagine that from a point source at towards a particular direction, a single linear drawing we kind of draw, and then how it's getting reflected we see. And this concept is only being like kind of extrapolated and then being used in softwares where they use the concept called as ray tracing. Basically, now also you can see ray tracing is a concept where it can be applied in sound and also lighting also. There's a common thing that's there. Another thing where before I was talking about absorptivity, when we consider a whole room, there is a time where actually sound kind of decays below a certain level. Like consider like this RT kind of calculates how much time it takes for sound to decay below a certain level. That is reverberation time. So we use the Seven's formula to actually find reverberation time. Uh, RT is equal to 0.163 by into 0.163 into volume divided by A, which is A is actually called as room constant, and room constant is also, it is measured in Sabins, and it is basically calculated using the uh, absorption coefficient of each particular surface and multiplying it by the particular surface area. Here for an example, small room example, we have a room of 5 meter by 4 meter with height of 4 meter. It will finally, it kind of has wall absorption coefficient as 0.3, floor as wall as 0.6, floor as 0.3, and ceiling as 0.4. It yields in RTF 0.228. And till this, I think I was telling in the last class. Further moving on, this chart kind of gives an overview of what is the optimal reverberation time for each purpose. Example, if we have something like, I hope you can see my pointer. Here if you have spaces like drama theater or high school auditorium, let's consider this high school auditorium. The recommended reverberation time is, it lies in the range between like 1.2 to 1.8. So to achieve that, there is also another graph in the bottom which is basically that the vertical axis shows the percentage of total surface area that is finished with absorption material and audience. So it kind of gives an indicator that if you have that particular space, you can refer it to utilize it and refer basically to find out how much percentage of the surface in the whole volume you should treat acoustically. So in this it kind of shows that around, if you treat like 35% of the whole space with proper absorptive materials, you can achieve that particular reverberance time. So basically, if you have like very recording and broadcasting studios, here the bottommost you can see, no, this is recording and broadcasting studios recommended reverberation time, which lies between like 0.2 to 0.7. So to achieve that, if we kind of drop a vertical line, and also based on this other part of these curvilinear lines are basically the volume of room that you have in hand. Like you have a very small volume, you kind of go below. For particularly you have a large recording volume which is up to like 1 lakh cubic feet. Here if you see, you rough to that particular point drop, you kind of draw another horizontal line. You can see that it gives around like 60%. So around 60% of the whole surface of the room you have to acoustically treat. Further, we were speaking in terms of the sound source and what is the time component, where like what is the reverberation time is basically the time to fade out. Here another point, we can design the space by adding absorption to a room so that it almost reaches a free field condition. Free field conditions where like you have no surface that kind of blocks, or like there's kind of a surface that blocks the sound, and it kind of makes the sound to reflect back. So if you we try to achieve in that manner. And acoustics is not all about applying sound absorbing materials, because if you have some spaces, there are spaces where you have to kind of uh, elevate the sound, or also to accentuate the sound you use reflective materials also. Example, sound absorbing materials is applied in like in a very quiet place, like reduce like to create a very quiet place, you use sound absorbing materials. Example, that recording studios will have very quiet spaces where like you have maybe a voice artist trying to record the sound, or a singer trying to sing, and then they use the singer's recording and utilize it in a music file. They actually go for maximum sound absorption possible, because there won't be any sound reflections coming back, and there won't be, it will be devoid of any sound defects. Another case where we have a meeting room or classroom where people speak, right? Like you should not get any echo, and we look into like various defects further. And sound reflecting surfaces where we use in spaces where we have mostly musical related things happening, where you want to bolster the loudness or accentuate the music's duration. It kind of helps in receiving the music in a good manner. When we look into conversation and meetings, we use one criteria called as speech intelligibility, where there are multiple indexes which you would have come across in the class. One is articulation index, which is kind of outdated now. Mostly what come places works here is speech transmission index and also speech intelligibility index, and these indexes vary from 0 to 1 or 0 to 100, and 1 or this 100 goes to a perfect intelligibility where you can crisply hear it. All these indexes what I am speaking in terms of speech intelligibility, it is from the perspective of the listener, not the source. Before we are looking into concepts where it is more oriented towards the source. Here this is from the listener's perspective. So if we have very high intelligibility, it means it is very easy to hear, but it might not be a good case where we should have the concept of confidentiality, where we when we take a open plan office, right, you don't want to hear other people so that you can concentrate on your work. And speaking of office, this is one study, a subjective survey has been conducted, and then this x-axis there are like multiple type of offices. The leftmost is the private office, and the rightmost is office, open plan office with no partition at all. And the office workers were asked questions like how satisfied or dissatisfied they are in terms of noise level, which is indicated in that white rectangle, and also sound privacy, which is indicated in the dotted rectangle. So in when we consider this open plan offices, most of them they were very dissatisfied with sound privacy. Last time when we are speaking about this speech intelligibility, this same concept comes into play here, where people were like morely dissatisfied in terms of speech privacy, but kind of they were neutral with the noise level in open plan office, because when we have an open plan office we always have that insecurity or a feeling where we try to avoid creating noise. Moving further, uh, the concept of clarity of sound. Basically, clarity of sound depends on the rate of sound decay. To maximizing, like we can increase the clarity of sound by maximizing both the direct sound and also the sound reflection that arrive. So for a very good clear uh, sound, clarity of sound, in when we consider the space to be used for speech purpose, we have this sound clarity index of 50 milliseconds. And if we go into the, if you consider the space like where music is being used, is the main purpose, the sound clarity index is uh, around 80 milliseconds. And this whole concept is called Haas effect. And here you can see, if you have a person speaking on stage, and then there is one, this D arrow, the arrow D shows the direct sound that is reaching the observer. But since the sound is kind of omnidirectional, in this it's not omnidirectional, but it scatters in multiple directions. One point source can kind of go hit the ceiling and hit the wall and again reflect back. So the same sound that was produced at one point of time, it's being reflected back and again reaches the observer. So if that particular time where the time difference between the d. You don't think in terms of distance, you think in terms of time. Example, it takes d time to for the observer to listen that particular first point source directly, and it kind of a plus b plus c together adds up, and then it reaches the observer again. So that particular point difference should be very less. This clarity index, this 80, is basically the difference between the direct sound and the reflected sound. If the difference is pretty low, it kind of creates a good perception of sound. You won't have this echo. If it takes very long to reach you, you will again hear the same sound, but at that point of time, the source would have spoken some other sound. Sanjeev, கொஞ்சம். So this clarity index gives an indicator. Utilize the clarity index to design a room. And also, speaking of room acoustics, when you consider a point source and a point of observer, here in this example, you would see, right, the direct sound source, it took to reach the receiver in 110 milliseconds. But after all this reflection, it took around 167 milliseconds. And the difference between the direct sound and the reflected path, it is 57 milliseconds, which is little bit not beyond the acceptable limit when we think that it is for speech purpose, but it is very much acceptable in music purpose case. Here, this is Boston Symphony Hall. This is considered one of a well-designed acoustical space that has been designed. Before, you would have been exposed to the concept of direct sound and reflected sound. Here, if you have this cross section of the room and also the view of the room, the hall. Okay, if you look at the graph here, the reverberance time kind of increases with the distance from the source, and after a particular distance, the reverberance time actually flattens. Basically, due to the design they made in such a way that the reverberance time flattens out, and since it is used for music opera kind of event, this 2 to 3 reverberance time is considered good. Look, when we look back into the optimal reverberance time, here you see, right, orchestra, chorus and all. Here the optimal reverberation time limit is between 1.8 to 2.6. Also, when we go further in detail how we design surfaces in an interior space, like light, sound also has this concept of specular reflection and diffuse reflection, where you have a very plain polished surface, hard surface, you will have specular reflection. And if you have this kind of a rough textured or undulated surface, it will result in diffuse reflection, where the intensity of the light, if you see this arrow, right, like imagine this arrow, big arrow, as a higher sound intensity level, higher sound pressure level, and it gets reflected in diffused case, and then it scatters at in different directions, and the actual intensity also kind of splits into smaller portions. Further, this is another concept where a study was conducted to find which is like psychologically what is the good setup for a listener. Like you have like 3 point sources. The arrangement of the 3 points was where kind of they used different type of arrangement. Here you can see, right, total 360-degree has been split into around like 15 16 sectors, and then the point sources have been assigned at multiple different places, and it was evaluated to find out which configuration will yield in the listeners envelope. Listeners, it's called the measure is called listeners envelopment. So the central one where you have a point source in front of the listener and two other point sources at the sides yield in highest envelopment. Moving further, uh, these terms all relate to acoustical defects. Uh, the first one is echo, where there is one point source, and due to that difference in the direct and the reflected point source at one particular point of time, echo is produced. Next concept is actually fluttering echo, where you have like two straight facing surface where the reflection happens again and again. So you have a continuous sound. When you go into an empty room, you will hear once you clap, it kind of continuously echoes. The echo will be like continuously there, and then slowly it fades away. That is flutter echo. And focusing is something where you have a concave surface, and you have a point source, and then the sound again gets reflected back to the same point source at multiple different time periods. So you have a kind of a prolonged elongated effect of that sound, which is undesirable. Another one is concave surface. Due to the concaving surface, there is a concept called as creep, which will result in hearing. Like example, there can be uh, a person like speaking. There's something happening here, uh, and I'll just show here. Yeah, here. If a sound source is being emitted, this place where the sound is being finally reflected back might not be an intended place where for hearing. Example, you have a dome kind of structure above you, and you're conversing with your colleague. Some person who is far away from you might be able to hear due to this creep effect. Other defects that also in a part of acoustical defects are excessive reverberance, loudness, acoustical shadowing, and resonance. Acoustical shadow is something where you see this balcony, right? If you have very elongated balcony, there might be listeners inside the space where they won't be able to receive the sound only. That's called acoustical shadowing. So moving further, we'll further talk about acoustical materials. acoustical material is kind of evaluated using concept of transmission loss. It's same also here also it works similarly with light and also heat, where you have a point source. This dotted line shows the point source at a particular decibel level, and some portion will get reflected, some portion will get absorbed, which is C, and some portion will get transmitted, that is D. So the interest in this particular point of time is D, which is the transmitted sound beyond the barrier. You have a barrier and how much sound is transmitted. So this transmission loss is calculated using the value tau, which is calculated D divided by the point source A, and using the tau you use this log calculation minus 10 log tau to find out the transmission loss. And there is also another simple measure called as noise reduction coefficient. In the starting of the session we already know the concept, like sound has different frequencies. Sound can be like produced at different frequencies, and each different frequency will have its own pressure level. So looking at into the material concept, the material also will have this absorption coefficient for each particular frequency. May like if you have a room where musical instruments are being played, they might be having a particular band. In my example, I'm saying that they are very low frequency band. So in order to give the sound barrier or absorptive material, you should look into materials absorptive coefficient relating to that particular frequency. And this noise reduction coefficient kind of gives an overall number to kind of go to which material you choose, instead of like instead to confuse people with multiple frequency related transmission coefficient. So this is like here you see, right, like it's basically takes noise reduction coefficient takes four different alpha values at frequencies starting at 250 hertz and which ends up at 2000 hertz, and taking an average out of them. And here this chart kind of shows the relation between the absorption coefficient of an area weighted room along with specific materials noise reduction coefficient. So if you have a recording studio for speech, you can use these particular materials, where you can have, if you use an acoustical tile, that will have around 0.7 noise reduction coefficient, and you have certain number of occupied occupants. Actually occupants, you see, they also have particular noise reduction coefficient of like around 0.7, because we are very good observers of sound also. So if you have a large gathering, the sound kind of easily fades out. So it is, you have to consider occupants also inside. All these concepts what we saw before, we took this uh, we took these concepts without considering the occupant in place. If you have all the audiences in place, you will also have certain noise reduction coefficient that you also should apply for calculation. Since it is kind of like mathematically hard, we go into softwares for these calculations. Moving further, there are like multiple different types of uh, absorbers that we use for acoustical treatment. One is panel, next is cavity, and another one is porous. Porous observers, as the name suggests, it has basically have very large air gaps in the material configuration. And panel observers basically are like a compact panel boards that you have. Another one is cavity observers, where you have in a panel you kind of make small perforations. You end up with cavity observers. Uh, Consider this chart. There are like two different charts in this presentation slide, where a different configuration of porous observers are compared upon. And if you can see to the left, you have the absorption coefficient associated to particular frequency. So if you have 1-inch porous observer along with shredded fiber board, it will have a very good absorption coefficient at higher frequency level of 2000 Hertz, which has absorption coefficient of 0.82. But when you go look into this lower frequency range, its absorption coefficient is pretty low. It's like 0.06. It's basically, it's not absorbing, it's basically all the sound intensity which is being directed upon will be almost all will be reflected back. But when you go below here, in this case where we have very high absorptive coefficients values, where you have very good values for all frequency ranges with different material. The other case, in this right side chart shows whether putting a carpet will yield in good sound absorption in the space, where it compares quarter-inch thick finished carpet and indoor-outdoor carpet, and multiple carpets are being thickness with different thickness are being compared. You can see that the absorption coefficient is gradually increasing at for only higher frequencies. For lower frequencies, you don't have much improvement at all. So carpet is a good recommendation for the sound sources at higher frequencies. And this data sheet gives the NRC value and also sound absorption coefficient for different materials. Next, we spoke about noise reduction coefficient. Another thing also we talk about is the sound transmission class, which is used. I spoke about transmission also before, where what is the transmitted sound level beyond a barrier. So these things are utilized to create barriers. In acoustics, there are like two different concepts you have to consider. One thing is you have one room and you have a space, and then the surfaces inside the space has to be treated in such a way that you will receive good quality of sound. Another thing is looking beyond the room. You have sound source in this room. The sound source might be or might not be desirable in the next room. So how you barricade the sound in a particular space so that it doesn't propagate into the outside space. So to measure that, these other values are being used. Here we talk in terms of sound transmission class, where multiple sound transmission class levels for each particular purpose of space is given, and The sound transmission class is basically it's kind of a specification, but how do you actually measure it? In if you kind of compare it in terms of fuel efficiency, where you have a vehicle, this transmission loss might be thought of as an what is being advertised. You have one car which they advertise like it gives 25 kilometers per liter, but what you actually measure, you might end up getting like 18 kilometer per hour, sorry, 18 kilometer per liter. So that is noise reduction. Noise reduction basically the sound level in the source room minus sound level in the receiver room. Moving further, these are the various softwares that are used in acoustics. The last one which I showed is it's not so validated, but for your own experimental reasons, like if you want to like explore it, it's a free software. You can download it and see what and analysis that can be done. All other things they actually are you have to buy them. Maybe you can also there are some software which allow you to do demo also. Moving further, we look into lighting. Lighting, you all know that light has a various wide spectrum of light. So it starts from cosmic radiation. When we just consider visible light, you have this small band between UV and IR range. And let me just talk about this concept of interrelationship between luminous flux, luminous intensity, illuminance, and luminance. Luminous flux is basically the total amount of light which is being emitted from a point source, and its unit is lumens. And luminous intensity is something where you put in the concept of direction and also a solid angle. Solid angle is something what you say solid angle is something like this dotted circle that you see, that is the solid angle where the amount of luminous flux emitted by a light source in a particular direction per unit solid angle is called luminous intensity, which is measured in candelas. And illuminance is something the amount of light that light flux that is received by a surface that actually falls on a surface. And usually we use this illuminance, which is the H as a unit lumens per meter square, to measure the lighting levels in rooms. Basically, all this daylight autonomy and daylight illuminance, we utilize these numbers to actually go for this green building certification also. So, illuminance is a major component that plays in achieving all these lighting levels. But if you see this, no, basically it is a measure of light falling on a surface, but it's not a measure what a person inside a user inside the space is actually perceiving. So the perceiving concept is the luminance part, where the ratio of the luminous intensity of a surface comes into play. Illuminance something like at a particular point, what is the actual light in candelas per meter square received at that point. And we also look into the concept of glare, where glare is lighting defect we try to avoid. And some things are not kind of covered in the whole portion, but I'm just trying to like give some kind of more understanding in terms of lighting, how you utilize it. So if you have there are like two different concepts like direct lighting and diffuse lighting. Direct light something that if you have one single point source, you will have sharp shadows falling around that object. That is called direct lighting. And diffuse lighting is the concept where you have multiple point sources which will yield in kind of diffusing the shadow. There is not much shadow you will be able to perceive. that will yield in diffuse lighting. Next, this concept of luminous efficacy, basically it's not covered in the subject, but it's used to measure what is the efficacy of a particular lighting based on its actual consumption of electrical power. And also when you look into light actually being like received, what is it is kind of assessed in using different measures, indexes. One is this light color rendering index, where color rendering index of 100 means that the spectral output will contain the entire visible light spectrum, ranging from the least wavelength to the last wavelength of like 300 something to 700 nanometers. The whole spectrum will be there. That's color rendering index. This is actually used in artificial lighting, where some bulbs or lighting device will have a particular range of color rendering index that you can look or refer to and then select them. Another one is the correlated color temperature, where you assess the lighting source whether it is warm, neutral, or cool. Neutral is something where you feel that it's in the not in the warmer range or also cooler range. You have kind of a perfect white light. Another thing, this there is a factor called as daylight factor. Daylight factor is something, it's a ratio between the illumination in present in the indoors and also compared to the outdoors. It depends on three different components: the sky factor, the external and internal reflected components. So that you have to consider. Till now, what is covered is comes under the subject, and I want to talk about two different concepts which is not covered in the subject, but it's useful for you to kind of measure, like for the whole overall space. There's these are like some numbers that you can utilize, that whether that place is well lit or not. One thing is daylight autonomy. It is the percentage of annual daytime hours that at a given point in a space is above a specific illumination level. Here, and it's basically measured in percentage. Here, if consider this rectangular or a square space, if you consider a threshold, actually you have to set a threshold value x. Here in this x example, here it has been taken as 300 lux illuminance. So this kind of configuration yielded in 53% of the whole floor area, above which 50% of the time you achieve illuminance value above 300 lux. Another case is useful daylight illuminance, where instead of using one single threshold value, you keep a range. Because like if the lighting illuminance level is like beyond like 2000, 3000, 4000 lux, it might not be appropriate for you. You don't need that much light also. Basically it might result in discomfort, so you put a range. Because daylight also, this and all you use it for daylighting. Daylight kind of is so dynamic, it varies throughout the day. You kind of set a range between 100 to 2000 lux, and using this range you find out that how much percentage floor area is achieving at least 50% of that daylight illuminance. I think this is my last slide. So for these are things I covered. Thanks for listening. So Any doubts you can ask now. This is the last session. If needed, maybe I can conduct another doubt clearing session just for half an hour next week if you have any other doubts. Thanks for listening. If you have any doubts, you can ask now, or else I'll close the meeting. Also, you can give your feedback also how the session was like, or if you want any improvement in the subject. As of now, this is a very small course where you have only 4 weeks of course content with basics of all this heat transfer, acoustics and lighting, which has been incorporated. Fine, then if you don't have any doubts, I will be closing this session now. Thanks for listening. You will get notification from NPTEL side whether if you have next session or not. All the best for your exams. Now I'm closing the session.